In example 6.8, we are asked to define a linear function, and there's some conditions. The first condition is that it has to pass through the point 2, -3, and we have the second condition that we have to be perpendicular to the line whose equation is given by y equals 1/5 x plus 6. So this is very similar to example 6.7, where we have an equation, but the equation that we're given is not going to be used to directly write our function, but instead we're going to use it to help figure out the pieces that are necessary for writing our function. So since it's linear, that tells me that the equation has to be of the form y equals mx plus b. So we need to figure out what slope are we going to use and what is the y-intercept that we're going to use for our function. So let's start with the equation that we were given, and I'm going to take a graphical approach again, and I'm going to look at the y-intercept plus 6, and the slope here is 1/5. So I can use that to get some points there in the first quadrant. I'll also go backwards with this to get several points in the second quadrant. So I have a line that goes across the first and second quadrant with the window that we're using. And that's the equation y equals 1/5 x plus 6. So for our function needs to pass through the point 2, -3, and we'll mark that, and it has to be perpendicular to the line that we just drew. So I'm going to do an estimation. It should be something similar to this. So it forms a nice 90-degree angle here at the intersection where the two lines end up crossing. Now again, this is just an estimate. This doesn't actually give me the slope, the exact version of the equation that I need. So when I think about the red line, the slope of the red line I can see is 1/5. Now I need another slope that's going to guarantee that I'm perpendicular. That particular slope is going to be the negative reciprocal of 1/5. So the reciprocal of 1/5 would be 5, or 5/1. And negative really just means the opposite of. So since 1/5 is positive, I'll need to make this one be negative. So the slope for my blue line needs to be -5. Now I will always encourage you to check this. So to check this, you're going to take the slope from the red line, which we can't change, that is set. And then we're calculating what we think the slope needs to be for the blue line. And if we multiply these two slopes together, we should always get -1. And if we do, then we know that we have selected the correct slope. So my equation should have y equals -5x plus b. So now I know the slope. And like on example 6.7, I can calculate the y-intercept by using the point that's provided. So I'm going to let x be equal to 2, y be equal to -3, and then that's going to tell me that -3 is equal to -5 times 2 plus b, which implies that -3 is equal to -10 plus b, and there's only one value of b that will make this statement true, and that is b needs to equal 7. So my equation is y equals -5x plus 7. So that's really the bulk of the work here, is figuring out that equation. So let me write a function. I'm going to use g this time. G from r to r given by g of x is equal to -5x plus 7. And that's what we're asked to define. So we worked the majority of this algebraically, but we did use a little geometry to help us start the process of understanding what the perpendicular lines would look like in our Cartesian coordinate plane. So I still don't have the exact picture here, and I think it would be useful if we did. So going back to the point 2, -3, if I use a slope of -5, I'll go down 5, right 1, and then I'll go backwards with that. I'll go up 5, left 1, up 5, left 1, and then I can draw the line. And that's going to be much more precise than what I originally started with, and I can see pretty clearly here that we have a 90-degree angle there. And I can also see that the blue line ends up crossing the y-axis at 0, 7, which would match the b value that we calculated over here, thus giving me some more confidence that the equation that I've written is in fact correct.